Okay. Yeah, thank you. That is essentially the leading, B3 is the leading data structure for majority of databases, Oracle, MySQL, Postgres, SQLite, right? These are all which use B3s. If you look at the B3s, they have a pretty good point reads, right? So if you do the read of a single row, right, of single value for a B3, it's pretty optimal, but they're also pretty expensive in writes, right? And we'll look into more details how that works. Now, the other quite common data structure is log-structured merge trees. These have been invented in 1996, so that is much newer data structure, have been around for about 20 years now. And there are also multiple implementations and variants exist, right? Sometimes you have like 2 levels. Sometimes you have more than that. And LSM-Trees, which is what is called write-optimized storage engine. They can take writes very, very effectively, pretty much independent on the amount of a data size which is stored in the LSM-Tree. But at the same time, for point selects and for reads doing the ranges on the data, they can be quite slow. There is also another relatively popular data store, which I will call like, well, no index, right? Where people are using some sort of a layout instead of actually building the index. Store data in some kind of chunks, and then if you need to retrieve the data, why don't we scan all those chunks probably in parallel, right, and get the data we need. Column storage engines, for example, doing that very frequently, right? Often also some form of partitioning is also being used, right? We're saying, hey, we're not only using data like column store, but we are partitioning data by day. So maybe we can't find all the rows between 2 o'clock and 3 o'clock, right, through index effectively. But we can go and scan all the data for 1 day instead of everything we have in a database, right? The approach for those data is typically, it is for those family of systems, is typically they are quite good with the bulk loads, right? Think about Hadoop or Vertica, right? But they may not be, and they're also efficient for large reporting queries, but not essentially for just single row lookup here and there. Now let's go in a little bit more look at what how the B3 indexes look like. And this kind of uses kind of sort of scientific notation, right? You have a B3 there, we call those internal nodes, which kind of lead us towards the data as pivots. So what a pivot is essentially, it tells us where to go and look up the data down below. For example, the pivot may have a value 5, which says, hey, everything which is less than 5 should go here, and everything which is more than 5 should go there, right? And then we also have a leaf nodes, which would contain the actual data, which is essentially sorted in those nodes. And if you have to make a lookup of the data in this given page, we can we can typically do like a binary search, but sometimes we have to scan the whole pages, right? So let's see what happens with a B3 if we have a tree like this, right? And we are looking to insert 15 into that, right? So it will go down to the very bottom of a tree, leaf nodes where data is stored. And even in the best case scenario, assuming there is enough data on this page, right? So we don't have to do a page split, it will have to modify the data on that page. Make sense? Now, if we do a search, well, we essentially do another descent. Now, what is the problem in this case? If our data is completely in memory, everything is good, right? We're just doing inserts, and we're all going through its data structures and store in get in memory. But in a lot of cases, when the data is large, you cannot get the whole tree in memory. What typically happens in this case is what typically their non-leaf pages of a tree are small enough so they fit in memory, right? And on your leaf pages, only some of them, often small portion, will be in memory. The rest have to be just on disk. Now, to explain why all the top part can fit in memory. Well, an amount of pointers here, which we only draw kind of a couple here, can be called fan-out, right? And depending on the index size, index length and the page size, the fan-out can be different, right? But what that fan-out does, it defines the ratio between essentially top pages in the RAM, non-leaf pages and the leaf pages. If you think about, for example, MySQL and B3 indexes in Innodb, your page size is 16K, right? If you would say our value, right, plus the pointer, like a primary key, together consists about 40 bytes, then in this case, we can fit how many? 400, right, values in that index. So there is going to be not 2, but 400 pointers, right? And that means there is going to be approximately 400 as little non-leaf pages as leaf pages, right? And that means what most likely everything for non-leaf pages will be in memory with high probability, right? So that's why we only analyze this, right? But anyway, so if you look at our case where data set is large, 10 times or more larger than amount of memory, then as I'm doing my writes for each insert, or I will have to do one physical I/O operation, which is actually quite expensive, right? So that means if you're looking at a B3, then often the I/O storage performance can be very, very important. Now, in this case, that is using a provisioned IOPS at AWS, right, with not provisioned IOPS. There is difference like about a 6x, right? The same difference you can say, hey, if I'm using some high-performance flash versus our kind of slow-spinning disk. The difference for the insertion can be quite significant. So now let's talk about the fractal trees. What is this data structure, right? How it works and how it's same and different compared to B-trees. Fractal trees indexes was invented in 2007 by some people from MIT, Rogers, and Stony Brook's university, right? So it was kind of a bunch of years of research in a way, how can we optimize this old data structure of a B-trees. And what it was looking at a couple of things. First is how can we balance this kind of between B-tree and LSM approach to sort of both have a high performance write speed and a decent read speed, right? How can we do that? Another thing is what fractal trees are focused on using modern hardware and operating system effectively. And what we have those days, we typically have a fair amount of memory. We have a lot of CPU cores, right, which are available to us, and so on and so forth. So if you look at the fractal trees, they are rather similar to B-trees from some extent. So we will have the same kind of internal nodes, right, and leaf nodes, and we would have those pivots. But what is different is what the data modifications are not implemented, applied to the data structure directly. Instead, they are thought as messages, right? So I essentially send a message like, hey, I want to insert the row, right? Or I want to update the row. And those messages are being stored in the buffers which apply to all internal nodes, right? And from that, they kind of they cascade down, right? So if the buffers are empty, you can see it looks exactly the same as a B-tree. And that is actually pretty good because what that gives us is that means then Fractal tree is sort of optimized if all the messages push down, then the read performance can be achieved very similar to a B-tree, right? We just go ahead and fetch one block, everything is in memory. Now, what happens if we insert a value 15? Well, it just goes in the buffer of a root node, right? Root node is in memory. So we are not doing any I/O whatsoever, right, in this case. And that can take, well, a lot of time, right? When this buffer fills, it will spill out the buffer below. Chances are it's also in memory. And essentially that means it will take maybe 100, right? Or some sort of large number of updates going to the same kind of target page for that finally to require that page having changes being applied. Now, what is interesting in this case is these messages can go beyond simply update of the data, right? We can also use that to do some other messages, right? You can see insert, deletes, but we can also push the changes of updates, right? Saying, hey, I want to increment the value, right, or multiply that. That can be stored in the data structure as a memory and applied sometime later down the road. Or we can even do the alter table, like add a column, push the message out there, and it will kind of gradually propagate and restructure tree down the road. But the schema change will be essentially instant, right? So now, if you are thinking, hey, that looks like a wonderful data structure, so where do we get it? Or what kind of software solutions really implement this data structure as well? One is the TokuDB storage engine for MySQL ecosystem, which is mainly available in Percona server and MariaDB. We also have TokuMX, which is a MongoDB compatible server, right? Just kind of complete solution. Then also TokuMX SE, which is a MongoDB storage engine for MongoDB 3.0. Now, if you are looking for something even more hardcore, there is the library called like TokuFT, which is essentially the BerkeleyDB compatible library, which you can use, right, to supercharge your BDB-like applications. So if you just look at the TokuDB in MySQL, because that is probably the most commonly used implementation, right, of Fractal trees those days. It gives you transactions and MVCC similar to Innodb. It gives you compression. You can get typically much more powerful compression with a lot lower overhead when it's Innodb. It gives you hot schema changes with no table kind of copying required, right? Innodb also allows you online alter table in, let's say, MySQL 5.6. But that requires copying the table, which is expensive and also means you have to have a double amount of disk, essentially, right, to be able to perform that operation. We get the clustered secondary indexes, read-through replication, and efficiency, right? These are kind of comparison of Innodb and TokuDB. I think what is important here is what TokuDB is not for everything. If you have all your data fits in memory, right, or majority of workload in memory, then you should not be using TokuDB. It will be slower. if you are really having a very large data set and it's write intensive, right, or some logic queries are prevalent, then TokuDB will often perform much better. Now, this is all we talk about the algorithms, right, and kind of the ideas. Well, we well know what it's possible to screw up any kind of decent algorithm implementation, right? So you need the good implementation as well as the great concepts. First one is TokuDB has been around for a long time, and we had done a pretty extensive QA with TokuDB and the store and Percona server. And I would say from my standpoint, that was a first not in the DB storage engine, which actually was pretty mature, right? Because most storage engines, they kind of, you can sort of create table, insert a couple of data, but if you really put them into the stress, they just fail. And TokuDB was pretty robust. So I would say that is the only other solid transactional storage engine beyond Innodb XDB. Now, another thing is we like this technology, right? And we worked as a partners with TokuDB, Tokutek team for a couple of years. And then 2 months ago, we acquired Tokutek, and now this is Tokutek